Good day. The topic of today's lecture is data aggregation and grouping. We will explore the fundamental SQL mechanisms that allow us to move from analyzing individual rows to calculating summary values, such as sums, averages, and counts, and learn how to group data to obtain subtotals.
Today, we will start by studying the basic aggregate functions that allow us to summarize data. Then we will move on to the most important part, the group by clause, which allows us to apply these functions to specific subgroups of data. Next, we will look at how to filter these groups using the having clause. And finally, we will discuss how to work with unique values using distinct in aggregation. In previous lectures, we worked with individual rows. However, in data analysis, it is often necessary to summarize information. Instead of a list of all students, we might need their average grade or total count. This is where aggregate functions come in. Unlike scalar functions, such as the upper function, which work with each row individually, an aggregate function takes an entire group of rows, processes them, and returns a single value. Today, we will look at the 5 main aggregate functions in the SQL standard. Before moving on to specific functions, let's look at the data we will be working with. This is the students table. Note that it contains the student ID, last name, faculty ID, faculty code, and GPA. It is important that Kovalchuk's faculty ID is null, which will affect some of our calculations. Let's start with the most common and perhaps most important aggregate function, count function. Its simplest and most common form is count asterisk, meaning count with an asterisk. The asterisk symbol here means all rows. Thus, count asterisk gives a simple instruction to the system: count the total number of rows in the set we are analyzing. Consider the first example. We want to know how many total students are in our students table. The query, select count asterisk from students, will return 6. The system simply looked at the table and counted all the physical rows in it. Now for the second, more practical example. We need to count how many students are studying in a specific faculty, for example, with faculty ID equals 1. Here, it is important to understand the logic of SQL query execution. First, the from students clause is executed. Then, the where faculty ID equals 1 clause is triggered. The system scans the entire table and selects only those rows that meet this condition. In our case, these are 3 rows: Petrenko, Sidorenko, and Bondar. And only after this, the aggregate function count asterisk is applied to the filtered set of 3 rows. It counts the number of rows in this temporary set and returns 3. So, count asterisk always counts the rows that passed the where filtering stage. Now let's look at the second form of the count function, count column name, where instead of an asterisk, we specify a specific column name. What is the key difference? If count asterisk simply counts rows, count column name first looks inside the specified column for each row. If that column has a null value for a particular row, count does not count that row. Let's look at our example. We want to count how many students have a faculty assigned to them. For this, we count faculty ID. The system reviews all 6 rows in the students table. Petrenko, faculty ID equals 1, not null, count 1. Ivanenko, faculty ID equals 2, not null, count 2. Sidorenko, faculty ID equals 1, not null, count 3. Kovalchuk, faculty ID equals null, ignore. Melnick, faculty ID equals 2, not null, count 4. Bondar, faculty ID equals 1, not null, count 5. Thus, the row for student Kovalchuk, whose faculty ID is not filled, null, was ignored. The query result is 5. This is a very useful function to understand how completely your data is filled. Finally, let's look at the third very important form of the count function, with the keyword distinct. This is a modifier keyword that we place inside the parentheses before the column name. Distinct instructs the system, before counting, first discard all duplicates. Let's compare all three forms of count function using faculty ID as an example. Count asterisk returned 6, total number of rows. Count faculty ID returned 5, number of rows where faculty ID is not null. Now count distinct faculty ID. What the system does, it looks at all values in the faculty ID column, 1, 2, 1, null, 2, 1. Distinct filters out null and all repeated values. The unique set of values remaining is 1 and 2. After this, count function counts how many elements are in this unique set. The result is 2. Thus, this query answers a completely different business question. Not how many students have a faculty, but how many unique faculties are represented in our table. This is a fundamental function for analytics. The next important aggregate function is sum function. Its purpose is very simple. It calculates the sum of all values in the specified column. It is important to remember two key points. First, sum function works exclusively with numeric data types. You cannot sum rows with last names or dates. Second, just like count column name, sum function completely ignores null values. They are not treated as zeros, they simply do not participate in the calculation. Let's look at the first example. Imagine we need to calculate the total scholarship fund paid to all students. Let's conditionally assume that the scholarship is GPA multiplied by 400. The query select sum GPA multiplied by 400 from students will take the GPA of each of the 6 students, multiply each by 400, and sum all these values. Note that we can use expressions inside aggregate functions. The result will be 10,200. Now for the second example, where we combine aggregation with filtering. We need the scholarship fund only for faculty ID equals 2. Here, again, where faculty ID equals 2 is triggered first. The system selects only 2 rows, Ivanenko, 3.9, and Melnick, 4.8. After this, the sum function is applied only to this filtered set. It calculates 3.9 plus 4.8 multiplied by 400, which equals 3,480. This demonstrates how where clause and aggregate functions work together. Where clause filters rows, and sum function summarizes what remains. We continue to study aggregate functions, and the next one is AVG function, which stands for average. It calculates the arithmetic mean for a set of values. Like sum function, it works exclusively with numeric data, and very importantly, completely ignores null values. Essentially, AVG GPA works as sum GPA divided by count GPA, not as sum GPA divided by count asterisk. If someone in our table had a null GPA, that person would simply not be included in the calculation. Let's look at the first example, the average GPA for the university. The system takes the GPA of all 6 students, since there are no null values in GPA, sums them, 4.5 plus 3.9 plus 4.5 plus 4.1 plus 4.8 plus 3.7 equals 25.5, and divides by their count, 6. We get 4.25. The second example demonstrates the same logic as in sum function. First, where faculty ID equals 1 is triggered, selecting 3 students, Petrenko, 4.5, Sidorenko, 4.5, Bondar, 3.7. Then the AVG GPA function is applied only to this filtered set. The system calculates 4.5 plus 4.5 plus 3.7 divided by 3 equals 12.7 divided by 3 equals 4.233. This is a powerful tool for quickly estimating average indicators in any data samples. We conclude our overview of basic aggregate functions with the pairs min function and max function. Their purpose is absolutely clear from their names. They find the minimum, smallest, and maximum, largest, values in the specified column. Like all previous aggregate functions we have considered, except count asterisk, They completely ignore null values during the search. An important advantage of min function and max function is their versatility. Unlike sum function and average function, they work perfectly not only with numbers. If applied to text strings, they will find the first and last values in alphabetical, or more precisely in the collation order defined in the database. If applied to dates, they will find the earliest and latest dates. Let's look at the examples. The first example is the simplest, working with numbers. We ask to find min GPA and max GPA. The system scans the GPA column, 4.5, 3.9, 4.5, 4.1, 4.8, 3.7. Finds the minimum value 3.7 and the maximum 4.8. The second example demonstrates working with text. Select min last name will return the last name Bondar. As in the Ukrainian alphabetical order, it comes before all other last names in the table. Max last name would return Sidorenko. We have covered the 5 main aggregate functions. They take the entire table, or all rows that passed where filtering, and compress them into a single result row. For example, count asterisk gave us one row with the number 6. AVG-GPA gave one row with the number 4.25. And here we encounter a fundamental and very logical limitation of the SQL standard. What happens if we try to ask for both an aggregated value and a regular column in one select query? Look at this incorrect query on the slide. Select last name, AVG-GPA from students. Let's try to imagine how a database management system, DBMS, should execute this. The system looks at the last name column. This column exists for each of the 6 rows, Petrenko, Ivanenko, Sidorenko, and so on. Then the system looks at AVG-GPA. This function is calculated once for all 6 rows and returns a single scalar value, 4.25. The DBMS faces a logical contradiction. It has 6 last names, but only one average value. Which of the 6 last names should it show next to this single value 4.25? Petrenko, Kovalchuk, or all at once? Due to this fundamental ambiguity, such a query is syntactically incorrect, and any relational database will throw an error. This limitation naturally leads us to the next big topic. What if we want to see not one average value for the entire table, but, for example, the average value for each faculty separately? For this, we need a mechanism that allows us to apply aggregate functions not to the entire table at once, but to its individual subgroups. This mechanism is the group by clause.
So, we stopped at the problem. SQL does not allow us to output last name and AVGPA in one query, because last name exists for each of the 6 rows, and AVGPA is one value for all. But what if our task is formulated differently? What is the average GPA per faculty? This is no longer one overall summary, but several intermediate summaries. It is precisely for this task that the group by clause exists. Group by is an instruction that fundamentally changes the behavior of aggregate functions. Instead of applying AVG function to the entire table at once, group by faculty ID instructs the system. First, take all 6 rows. Create separate logical buckets for each unique value in the faculty ID column. We will have a bucket for faculty ID equals 1, a bucket for faculty ID equals 2, and a bucket for faculty ID equals null. Distribute all rows into these buckets. Petrenko, Sidorenko, Bondar will go into bucket 1, Ivanenko, Melnik into bucket 2, Kovalchuk into bucket null. And only now apply aggregate functions such as AVGPA or count asterisk to each bucket separately. Finally, return one summary row for each group. Thus, we will get not one general result, but 3 rows, one for faculty 1, one for faculty 2, and one for those without a faculty. Let's see group by clause in action. Our task is to count how many students belong to each faculty.
If we simply wrote count asterisk, we would get 6, which is not what we need. Look at the query. We ask for 2 columns, faculty ID, to know which group we are seeing, and count asterisk, to know how many students are in that group. But the key instruction is group by faculty ID at the end. Let's break down the execution logic of this query step by step. From students, the system takes all 6 rows. Group by faculty ID. The system scans the faculty ID column and finds 3 unique values, 1, 2, and null. It creates 3 logical buckets. Group 1, faculty ID equals 1. This includes Petrenko, Sidorenko, Bondar. Group 2, faculty ID equals 2. This includes Ivanenko, Melnik. Group 3, faculty ID equals null. This includes Kovalchuk. Select count asterisk. Now the aggregate function count asterisk is applied to each group separately. For group 1, count asterisk counts the rows and gets 3. For group 2, count asterisk gets 2. For group 3, count asterisk gets 1. Final result. The DBMS returns 1 row for each group, combining the value by which it was grouped, faculty ID, with the aggregation result, student count. As you can see, null is treated as a separate full-fledged group. We clearly see that we have 3 students in faculty 1, 2 in faculty 2, and 1 student whose faculty is not specified. Now that we are using group by clause, we can correctly mix regular columns, like faculty ID, and aggregate columns, like count asterisk, as we saw on the previous slide. But this only works if we follow one but very strict rule, which is fundamental to SQL. The rule is, any column in the select clause that is not an aggregate function must be specified in the group by clause. Let's understand why. Imagine our previous query that grouped by faculty ID. For faculty ID equals 1, it compressed 3 rows, Petrenko, Sidorenko, Bondar, into 1 summary row. If we try to trick the system and add the last name column to select clause, the same ambiguity arises that we discussed earlier. Which of the 3 last names, Petrenko, Sidorenko, or Bondar, should the system show in this single summary row for group 1? There is no logical answer to this question. Therefore, the DBMS requires clarity. In select clause, when group by clause is present, only 2 things are allowed to be output. The results of aggregate functions, because they return 1 value for the group by their nature. The columns by which we are actually grouping, because their value is the same for every row within that group by the very definition of grouping. Our previous query, select faculty ID, count asterisk, group by faculty ID, was correct because faculty ID was in group by clause and count asterisk is an aggregate function.
The group by clause is very flexible. It does not limit you to 1 aggregate function per query. You can simultaneously calculate as many aggregates as you need to analyze each group. Let's consider a practical task. We need not just 1 indicator, but a complete profile for each faculty. How many students are there? Count asterisk. What is their average GPA? AV GPA. What is the highest GPA? Max GPA. What is the lowest GPA? Min GPA. We simply list all these aggregate functions in select. Group by faculty ID will work as before. It will divide students into 3 groups, 1, 2, null. But now, for each of these groups, the system will apply all 4 aggregate functions simultaneously. Look at the result for faculty ID equals 1. Count asterisk equals 3, Petrenko, Sidorenko, Bondar. AV GPA equals 4.5 plus 4.5 plus 3.7 divided by 3 equals 4.233. Max GPA equals 4.5. Min GPA equals 3.7. This allows obtaining a very meaningful analytical data slice with a single query. I also added order by to the example for the result to be sorted and more readable, although this is not directly related to aggregation.
We can make our grouping even more detailed. Group by clause is not limited to 1 column. we can specify several columns, and in this case, the system will create buckets for each unique combination of values in these columns. Let's consider an example. Our task is to count how many students have the same GPA within one faculty. We no longer need just groups like faculty ID equals 1 or faculty ID equals 2. We write group by faculty ID GPA. Now the system looks for unique pairs of values. Petrenko, faculty ID equals 1, GPA equals 4.5. Create group 1, 4.5. Ivanenko, faculty ID equals 2, GPA equals 3.9. Create group 2, 3.9. Sidorenko, faculty ID equals 1, GPA equals 4.5. Group 1, 4.5 already exists. Add him there. Kovalchuk, faculty ID equals null, GPA equals 4.1. Create group null, 4.1. Melnick, faculty ID equals 2, GPA equals 4.8. Create group 2, 4.8. Bondar, faculty ID equals 1, GPA equals 3.7. Create group 1, 3.7. As a result, we got 5 unique groups. Now count asterisk is applied to each of them. Group 1, 3.7. Count asterisk equals 1. Bondar. Group 1, 4.5. Count asterisk equals 2. Petrenko, Sidorenko. Group 2, 3.9. Count asterisk equals 1. Ivanenko. Group 2, 4.8. Count asterisk equals 1. Melnick. Group null, 4.1. Count asterisk equals 1. Kovalchuk. As you can see from the result, we clearly identified that in Faculty 1 there are 2 students with the same GPA of 4.5, while all other students in their groups, Faculty ID GPA, are unique.
So, we learned how to filter individual rows using where clause. For example, where GPA is greater than 4.0. We also learned how to combine these rows into groups using group by clause and calculate aggregates for them, such as count asterisk. Now the next logical question arises: how do we filter the groups themselves? Imagine the task: show only those faculties that have more than 2 students. Our first intuitive attempt, based on our knowledge of where, would be to write where count asterisk is greater than 2. But this query as shown on the slide is incorrect and will lead to a syntax error in any DBMS. Why does this happen? The reason lies in the logical sequence of SQL query processing. Simply put, the where clause is executed before grouping, group by clause, occurs, and consequently before aggregate functions, count function, AVG function, etc. are calculated. That is, at the where stage, the system simply does not yet know what count asterisk is because it has not yet started grouping rows. At this stage, it operates only on individual rows. To solve precisely this task, filtering based on aggregation results, the SQL standard introduces a specialized new clause for us: having. Having clause is syntactically similar to where clause, but it works after group by clause and allows applying conditions to already calculated aggregated results.
The error with count asterisk in where clause arises because we are trying to violate the logical order in which the DBMS processes a query. This sequence is conceptual, not necessarily how the system physically executes the query, but it defines what is available where. Look at this sequence. First, from clause and join clause gather all the data. Then, where clause, step 2, goes through each individual row and decides whether to pass it on. Only those rows that passed where clause proceed to step 3, group by clause, where they are bundled into groups. After forming the groups, at step 4, aggregate functions, count asterisk, avGPA, etc., are calculated for them. And here's the key point. Where clause is executed at step 2, and count asterisk is calculated at step 4. At the time where clause is executed, no count asterisk for a group simply exists yet. Now look at having clause. It is at step 5. It is executed after group by clause, step 3, and after aggregate calculations, step 4. This means that at the having stage, the system already knows what count asterisk is for each group, and therefore having clause can freely use aggregate functions for filtering.
Now, let's write the correct query for our task. Display faculties where more than 2 students are studying. Look at this code. It is almost the same as our previous incorrect example, but with one key difference. Instead of where, we use having. Note the syntax. Having comes after the group by clause. This perfectly matches the logical execution sequence we just discussed. Let's go through the steps of how the DBMS will execute this query. From students plus group by faculty ID, the system, as before, creates 3 groups and immediately calculates aggregates for them. Group 1, faculty ID equals 1, Petrenko, Sidorenko, Bondar, count asterisk equals 3. Group 2, faculty ID equals 2, Ivanenko, Melnik, count asterisk equals 2. Group 3, faculty ID equals null, Kovalchuk, count asterisk equals 1. Having count asterisk is greater than 2. Now that all groups are formed and their aggregates calculated, having clause begins its work. It checks each of these 3 groups. Group 1, count asterisk equals 3. Condition 3 is greater than 2? Yes, this group passes. Group 2, count asterisk equals 2. Condition 2 is greater than 2? No, this group is filtered out. Group 3, count asterisk equals 1. Condition 1 is greater than 2? No, this group is filtered out. Select. Only the group that passed the having filter goes into the final result that the user will see. Therefore, we see only faculty 1 with a student count of 3 in the result. Groups with faculty ID equals 2 and null were correctly excluded by the having clause predicate.
Let's clearly summarize the fundamental difference between where and having. This is one of the most important rules in SQL, often confused by beginners. The whole difference is in the execution time. Where clause is an input filter. It triggers before grouping. It examines each individual row from your table and decides, will this row participate in grouping at all? If you write where GPA is greater than 4.0, the system will filter out all students with low grades even before it starts forming faculty groups. Having clause is an output filter. It triggers after the rows have already been divided into groups and aggregates, count, average, etc. have been calculated for these groups, and having checks these ready-made groups themselves. Accordingly, if you need to filter data by a regular column, even if you are grouping it, do it in where. This is more efficient as it reduces the amount of data for grouping. And if you need to set a condition on the result of aggregation, average value, count, sum, only the having clause is syntactically permissible for this. Both of these clauses can, and often will, coexist in one query. Now, let's look at an example that combines both filtering clauses. This perfectly illustrates their different roles. Our task? We want to identify faculties where the average GPA is very high. But we are not just interested in the average GPA. We are interested in the average GPA, AVG GPA, only among those students who already have high academic performance, i.e., GPA greater than or equal to 4.0. And this average GPA of the best must be higher than 4.3. There are 2 stages of filtering here. Row filtering. First, we need to filter out all students we are not interested in. This is done by where GPA is greater than or equal to 4.0, Ivanenko 3.9, and Bondar, 3.7, will not be included here. Group filtering. Then we need to check the average GPA of the faculties, calculated only from the remaining students, and filter the faculties themselves. This is done by having AVG GPA is greater than 4.3. Let's see how this is executed. Where clause. Out of 6 students, 4 remain. Petrenko, 4.5, Sidorenko, 4.5, Kovalchuk, 4.1, Melnik, 4.8. Group by clause. These 4 rows are grouped. Group, faculty ID equals 1, Petrenko, 4.5, Sidorenko, 4.5. For them, AVG GPA equals 4.5. Group, faculty ID equals 2, Melnik, 4.8. For him, AVG GPA equals 4.8. Group, faculty ID equals null, Kovalchuk, 4.1. For him, AVG GPA equals 4.1. Having clause. Now these 3 groups are checked. Group 1, 4.5 is greater than 4.3? Yes. Group 2, 4.8 is greater than 4.3? Yes. Group null, 4.1 is greater than 4.3? No. This group is discarded. Result. We see only faculties 1 and 2.
We have already encountered the keyword distinct before. We used it in select distinct to remove complete duplicate rows from our result set. Today, we will look at its second, no less important role, distinct as a modifier inside aggregate functions. The most common and fundamental application is count distinct column name. This construct allows us to clearly differentiate the semantics of our queries. Let's compare. Count asterisk asks, how many total rows? In our example, 6. Count faculty ID asks, in how many rows is the faculty ID field filled, i.e. not null? We remember that Kovalchuk has null, so the result is 5. Count distinct faculty ID asks, how many different, unique, values exist in the faculty ID column, ignoring null? Let's look at the example on the slide. Count faculty ID sees the set of values 1, 2, 1, 2, 1, ignoring null, and returns their count, 5. Count distinct faculty ID looks at the same set 1, 2, 1, 2, 1. First identifies the set of unique non-null values, which is 1 and 2, and then counts the number of elements in this set. The result is 2. Thus, we see that we have 5 students distributed among 2 unique faculties. The power of distinct in aggregates is revealed even more strongly when we combine it with the group by clause. This allows us to conduct a very deep analysis of each individual group. Let's consider the task. For each faculty, we want to know 2 things. How many total students are studying there? This is simply count asterisk. How many unique GPA values occur among students of this specific faculty? This is count distinct GPA. How this query is executed. Group by faculty ID creates 3 groups, 1, 2, null. Then, for each group, both aggregates are calculated. Let's take the group faculty ID equals 1 as an example. It has 3 students, Petrenko, Sidorenko, Bondar, so count asterisk equals 3. Now let's look at their GPA, 4.5, 4.5, 3.7. Count distinct GPA finds the unique set, 4.5 and 3.7. The number of elements in this set is 2, so unique GPA scores equals 2. As a result, we see that although Faculty 1 has 3 students, they have only 2 unique GPA scores. This is a much deeper analysis than we could do before. We have covered count distinct, which is the most common case. However, the SQL standard allows using distinct with other aggregate functions, specifically sum and AVG. When you write sum distinct column, the system first, as in count, finds the set of unique non-null values, and then sums the elements of that set.
This is used quite rarely, but can be useful in specific financial or statistical calculations, where, for example, repeated transactions should not affect the final aggregate. Consider a simple example on the slide. You have a column with values 1,000, 1,000, 2,000. A regular sum column will give 1,000 plus 1,000 plus 2,000 equals 4,000. But some distinct column will first find the unique values 1,000 and 2,000, and only then sum them, giving a result of 3,000. The same applies to AVG distinct column. Finally, it is worth noting that although you can write min distinct GPA or max distinct GPA, it is semantically redundant. The minimum or maximum of a set of values will not change if you remove duplicates from it. The lowest GPA will be the same, regardless of whether one person has that GPA or 5 people do.
Thank you for your attention. This concludes our discussion on aggregation and grouping. These are fundamental tools that you will use in 90% of your analytical queries. See you next time.